I hope the espresso was very active and it helps you sort of get through this talk. So I'm going to be talking about an introduction to electromigration. So if you know all about it, you can sleep through the first few slides. If you don't, this is a basic introduction. The paper has been updated because I do things at the last minute. My slides were ready this morning. My paper was ready a few days after the deadline. So there were some typos that have been fixed, and the update is on archive as shown here. So first things first, I think congratulations to Jens, who has been a really important figure in this area, and these are some of his contributions to ISPD and beyond in this area. So thank you for helping the community with this. So for those of you who are not named Jens, this is a basic introduction to what electromigration is. It is exactly what it sounds like. It's migration of metal atoms due to electric current. And fundamentally, it's an interaction between two forces. There's a force that corresponds to oops, this is the wrong slide. Okay. There's a force that corresponds to the electron current that flows from the anode to the cathode. And then as atoms move from this side to this side, there's a concentration imbalance, which means that they tend to drift backwards, and that's the so-called backstress. And the idea is that if you have enough atoms migrating away from the cathode, then you create what's known as a tensile force, which again it's exactly what it sounds like. You're pulling things away from there, and it can create a void when you go beyond the elastic limit. A void is bad because that creates a break in the wire, and so you don't have electrical connectivity. So this is a picture that shows what it actually looks like. And the most important thing to kind of remember is that in today's technologies, where you use copper interconnects, every metal layer can be organized or can be analyzed independently because there's this barrier layer between elements that's shown over here. And this barrier, I'm not very good at this, I'm sorry. This barrier layer over here prevents metal atoms from going even through vias to the next layer. And this, in some sense, simplifies the problem, but in other senses, it makes it sort of more interesting. Okay. So my slides are pretty voluminous. I'm not going to go through all of it. And so what I've tried to do is to highlight the things that I really want to talk about. Conventionally, the way that you analyze electromigration is through this empirical equation called Black's equation. And what it fundamentally says is that the time to failure depends inversely on the current. So high current, fast failure. Right? So the way that you try to regulate this is you limit the current, or actually the current density to be more precise. So if you have high current, make the wire wider, and that's going to reduce the current density. There's also this other factor called the Black criterion, which says that if your wire is either very short or if it has a very low current, then the forward force, the electron wind force, and the backward force due to backstress balance out, and you'll never reach the point where the wire breaks. So there's actually a theoretically derived criterion for this, which says that the product of the current density and the length should be less than some constant, which is sort of material dependent. The other thing to take away from this is the fact that if you look at the current density limit according to this depends on various things. It depends on the temperature. It depends on the market segment that you're looking at. And so depending on the market segment, you might have different requirements on the number of power on hours, which goes from 20K to 200K. And the max temperature limit may also be different. So automotive is generally more stringent than consumer, for instance. So all of these dictate the requirements that you have, and these dictate the current densities in the conventional way that these have been analyzed. Now, this conventional approach, which says limit the current density, unfortunately has some issues. This was some work from TI about 15 years ago, which shows that if you have two wires of this sort, and this has a current density of J, and this has a current density of 2J, and this is directly downstream of this is supposed to fail sooner because it has the higher current density. But what actually happens is that this one fails sooner, which is this one over here. The time to failure actually is quicker for this one. So purely living with current densities doesn't actually explain this thing, but there is this alternative universe of so-called physics-based models which explain it really easily. So if I take the same wire with J and 2J, you can actually show that the stress buildup looks something like this, and the stress in this wire builds up on the stress that has already been built up over here, and so this high positive tensile stress actually causes a break in the wire over here, even though it has the lower current density. Okay, so since we have to show some equations, we may as well look at this. This is a fairly simple second-order partial differential equation that defines this thing. Because wires are very long, it turns out that a 1D approximation is good enough, which makes life a lot easier than, for example, Pritz's sort of a universe where you're looking at fluid dynamics. What that also means is that you can actually do things more easily in this. So for instance, there's a physical meaning to each of these terms. This is the back stress force because of the concentration gradient. This is the electron wind force, which is actually a negative sign not shown here, and they oppose each other, and at balance, this actually ends up becoming a sort of a DC condition. So this was analyzed by a guy called Korhonen in 1993, and actually many people before that too, but he wrote a really nice formalization, and he had some sort of nice interpretations of this. So if you have a semi-infinite line, then the stress builds up on the line over time at the cathode, and at some point, it's going to go over the sort of elastic limit, and the wire will break. If you have a wire that's not semi-infinite, but it's actually limited at both ends, then what happens is that the stress sort of builds up symmetrically over here, and eventually it reaches the straight line stress, which corresponds to the sort of the DC case where d by dt equals 0. And effectively what it says is that this term is 0, so del sigma by del x is a constant, which gives you this straight line over here. Okay? Now, I'll skip through this thing over here and just jump to this other slide over here. Now, when we talk about current going through a wire, it can go in one direction or it can go in both directions. If you have a signal line, during half the clock cycle or during half the duty cycle, you are charging up the wire, you're charging up the load capacitance. During the other half, you're discharging it, so the current goes backwards and forwards. And that doesn't necessarily mean that things cancel out. They don't actually exactly cancel out. But it turns out that if you look at the lifetime for DC electromigration versus AC electromigration, that's actually shorter for DC electromigration. If you have both directions, then it actually lasts longer because you have some restoration of the metal atoms that migrated and they come back, but they don't come back perfectly. Now, if you talk to foundries, they have specific ways of creating test structures, and some people at foundries, not all, will tell you that this is a non-issue because their test structures say that it's a non-issue. But in practice, what actually happens is that your forward current may not be the same as your reverse current. If your NMOS and PMOS are imbalanced, then you may have different currents, and then eventually there is actually a net migration from left to right or right to left, as the case may be. So what has changed over the last few years? This problem has been around forever. If you go to, say, something like IRPS, the Reliability Physics Symposium, people have been looking at this for decades. It's relatively sort of greater interest in the EDA world in recent years. And some of the things that have changed in the very recent past are that there are now linear time solutions that are available for those partial differential equations, which when you actually see them, turn out to be fairly obvious. And moreover, there are some mechanisms that give you physical insights which help engineers to think about these things, because this is fundamentally a mechanical phenomenon, and at least speaking for myself as an electrical engineer, it takes some time to sort of get used to the mechanical world. The unfortunate thing is that most PDKs are still geared up for empirical EM analysis, electromigration analysis. And this is in spite of the fact that, as we saw earlier, there are cases where lower current density wires can die before higher current density wires. And so there is kind of a desire to at least move beyond this at some point. Okay, so there are two ways in which you can solve this problem. The first way is the so-called steady state solution. What happens when everything settles down? So as we saw earlier, the electromigration in a single wire segment, the stress increases something like this, and eventually it reaches steady state. And if the steady state value is less than the critical stress at which you create a void, then the wire is supposedly immortal. In other words, it's never going to reach that breaking stress. If it turns out that this is above the critical stress, then at some point when it crosses the critical stress, it's going to break. Okay? So that's sort of fairly straightforward, but the DC solution is really something like this. What does this look like? And if we can see whether this is below the critical stress, then we can say that the wire is immortal. And at this point, what basically happens is that the partial derivative of the stress with respect to x is a constant. In other words, the slope is a constant. Now, given this insight, you can actually sort of work backwards, and you can figure out what the stress is going to look like exactly. So all of this text over here you can ignore. Let's just look at this picture. Let's say at the left end, I somehow knew that the stress was some value sigma 1. I know that this is a straight line going from here, which is proportional to the current, and there's a known constant of proportionality. So I know the slope of this thing. This is proportional to length, so I can figure out what sigma 2 is here. I know the current in this segment, so I know the slope over here, which is this, so I can basically multiply it by the length, and I get this value, and so on and so forth. So if I somehow knew this, I could predict this thing exactly. Okay? So in other words, what you can see is in a structure like this, you can do this in linear time. It's really not a big deal. The problem is how do you get this? And that comes from the idea of conservation of mass, which says that you're moving metal atoms here and there, but the total number of metal atoms is exactly the same. So that translates into saying that the integral of this is going to be 0, so the blue area is equal to the orange area. And that is what gives you the value of the sigma 1. So between this and the slopes, you've perfectly created the solution to this in linear time for the steady state. And then you can say, well, if this is less than the critical stress everywhere, the wire is immortal. If it's not, then you need to perform transient analysis to see when it dies. Okay. The other sort of interesting thing is that this product of J times L, which we saw before in the Black criterion, is really important, because it turns out that you can show that through a very simple derivation, that if I look at the product of J times L, it's proportional to the voltage drop along the wire. So remember, when you're trying to sort of optimize a power grid, for instance, power grids have unidirectional currents and are very susceptible to electromigration. You're looking at the total voltage drop, which is the drop across this wire plus this wire plus this wire, et cetera, which is the same as the JL product for this plus the JL product for this plus the JL product for this, et cetera. So in some sense, minimizing IR drop is correlated to improving electromigration reliability, because you sort of minimize this, but it's not identical, and the specific details are provided in the paper. Okay. So moving on from steady state analysis to transient analysis, now we have the same equation over here, and we want to find a solution to this. It's really not that complicated. It's a fairly well-known second-order differential equation. There's an infinite series solution to this that was proposed. It was listed over here, but was probably found even before that. And you can do something like this. The problem with this is that, well, what do you do with an infinite series? You're not going to evaluate all infinite terms, are you? So you need to figure out if you can sort of truncate it somewhere. So people had looked at this, and they did it in an ad hoc way. But it turns out that if you look at this a little more carefully, it's not that different from the telegrapher's equation that you see for transmission lines, for example. So if you use that analogy, there's a way of trying to think about it. If I have a wire of this sort, then I can think about a signal that starts over here, which is because of the electron wind, and this basically transmits over time this way. When it reaches the other end, it bounces back. There's a first reflection and a second reflection, and this is what you see in transmission lines. The same thing happens here as well. In fact, what you can see is that there's actually also another signal that goes from the right to the left, and this moves to the left here, bounces back, et cetera. And when you take the superposition of this as this semi-infinite line plus this semi-infinite line, and you add up these responses, that actually predicts the solution exactly. And you can actually do this kind of in a closed form, even if you have a straight line. So it's really simple to do this. And so to give you an example, remember that this is what we expect to see as the evolution of stress in the wire. So early on, if I look at the wave, the stress wave going to the right, it looks something like this. If I look at the stress wave going to the left, it looks something like this. And that gives me a sum that's something like this, which is similar to this thing over here. If I keep doing this for a longer time, then in this case, the reflection basically is 0 because it dies down by the time it gets here. But here, there is a significant reflection because the stress has increased. And if I add these up, I actually get the straight line that I associate with the steady state. So there's a really nice interpretation once you get into this thing. Well, real life means that lines are not just single stubs going from one end to the other. It looks something like this in a single layer. Remember that only one layer matters at a time. There are vias over here. You might have currents injected through these vias, so the current here may not be the same as the current here, et cetera. No problem. Think about it in the same way. At any point of discontinuity, you introduce a stress wave. So from here, you go to the right. From here, you go to the right and the left, et cetera. And so you have 6 points of discontinuity here, 0, L1, L2, L3, L4, and L5. And you can kind of draw the stress waves for all of these. This is actually pretty much a closed form term. And if you add these up, what you get is something that looks like this. And you solve it numerically, you get exactly the same thing. Okay? No big surprise because you're solving pretty much the same equations. But you can do this in linear time in the number of discontinuities. Okay? So currently, this approach works only for straight lines. We have ways that we know of to extend it to lines with branches. But there are other ways of interpreting this as well. So our first interpretation was think about it as a transmission line and use that inside. The second interpretation was, well, if you look at the heat equation, that has also been thought of as being equivalent to a transmission line. And there's this classical electrical thermal analogy that says that if you have, you're solving the heat equation, then you have a thermal conductance, which is like a resistance. You have a thermal capacitance, et cetera. Well, if these two are so similar, you should be able to do exactly the same here as well. And sure enough, you can. The stress equation looks something like this. It looks very similar to this. This is the role of the kappa over here. The V is the stress sigma. And so you can actually think about this equivalence. You can create an equivalent circuit for the stress equation with capacitors, which look something like this, resistors, which look something like this. And by the way, this is very intuitive because it's 1 over conductivity, which is sort of like the resistivity times the length divided by cross-sectional area, rho times L divided by A, right? So it's very familiar, and you can sort of translate something like this into something like this. Well, no excitations yet, right? How do you solve something that doesn't have excitations? Well, you have boundary conditions associated with any partial differential equation. Those boundary conditions are actually very interesting. So stress is continuous when I go from one segment to the other. Well, so is voltage in a wire. Flux is continuous. That is like KCL. And in this case, if this current is not the same as this current, then at this junction point, I'll add a current source, which ensures that I have KCL satisfied. Similarly, at the end point, I add a current source that ensures KCL is satisfied. So it's really simple to construct this. And now we are in familiar territory for electrical engineers. In fact, we can even use model order reduction. And we know that we can solve RC circuits with these excitations in linear time, right? So this is sort of the beauty of it, that if you just spend some time looking at it, you can translate it into a world that is sort of more familiar, and you can use the insights that you are familiar with to leverage this. And basically, with all of this, steady state analysis, transient analysis can now be done in linear time for physics-based equations. Okay. This is kind of just an example of what this looks like. This is the order of the reduced order model. And you can see that as you go from a lower order model, you have some inaccuracies here, to a higher order model, you get kind of pretty accurate solutions. Okay. Now, the interesting thing over here now, one of the things I've tried to do in this paper is to point out the things that you don't really hear about very much in other papers. So for instance, if you remember, I'd shown this picture earlier, and I said, well, the stress increases monotonically and it settles over here. And if this is less than the critical stress, then you're all good. This works perfectly for a single segment line with just one structure like this. But if I have multiple segments, so I have one segment here, one segment here, one segment over here, turns out that this DC solution is not an upper bound. And I'll show you an animation here. Last night, I sort of used, inspired by the talks here, I used Gemini to write some code that generated this thing. And I'll just run this animation. And you can see over here that this is the critical stress here. This thing sort of nudges up over here. And now, over time, as this goes up, this is going to fall down, and it's going to go below the critical stress. So the DC stress looks something like this. But during the transient response, it actually went above the critical stress, and guess what happened at that point? The wire broke. Right? So this is no longer an upper bound, and this is not, something you'll never find in any textbook or any paper that I've seen, at least. Right? So these are things that you have to be careful about. OK, so now we are experts at analyzing a single wire. A single wire is not much use to us. We have systems with billions of wires. So what do you do with these larger systems? The traditional approach was the so-called weakest link methodology, which is probability 101. If P is the failure probability of one component, then 1 minus P to the n is the probability that n components are failure-free, and 1 minus that is the failure probability of the system. Right? This assumes that all failures are independent. It assumes that a single failure leads to the demise of the whole system. But that's not really true. Look at a clock mesh. If I knock off one wire, yes, maybe my skew will get a little worse, but the system will still function, and maybe the skew doesn't go so bad. Look at a power grid. If one of these things gets knocked out, the power grid is still functional. It may just have a slightly larger IR drop. It may still be within specs. And in fact, if you look at the sort of the cumulative percentile, because this is a probabilistic phenomenon, you can see that if at the 5-year time point, the probability of failure is actually something like this. At 10 years, it's something like this. At 20 years, it's something like this. So you really need to analyze systems in a more careful way than this approach, which was sort of used a while ago. Now, everybody knows this. You talk to a designer. Designers are not stupid. They know all of this. But we've never had a way of kind of concretely analyzing this. OK. A few words about some open problems in this area. So remember, I said this earlier, that this JL quantity is really important, and there's a relationship between JL and IR. So if I'm optimizing a power delivery network, I'm typically optimizing the summation of the voltage drops along every wire. So if these are the pads, and these are a couple of layers of metal, and I have current sources in here, I'm looking at reducing the IR drop. Well, that is consistent with reducing the summation of JI Li. So in fact, I can actually say that this is really what dictates whether electromigration failures occur or not. And so I can create formulations that combine PDN optimization with electromigration optimization. The other way of thinking about this is, what's the solution? For both of them, if you have a high IR drop, widen your wire and reduce the resistance, or widen your wire and reduce the effective current density. So it's all consistent, and you can actually combine these things together. Another thing that has been sort of looked at is that, and it's done informally, is that if I have sort of a large current density over here, then I run out of a supply of metal atoms over here, and that causes a void. I can create a separate bank of metal atoms over here. I can create a stub over here, and that stub will provide metal atoms even when this is depleted, and so this will fail kind of later than this one over here. However, this has physical design implications, because now you need to allocate a space for the stub, et cetera. So where do you want to allocate it? How do you do it in a good way? The third thing, which has been slightly looked at, is this idea of electromigration being a one-way street. It's always been thought that, well, once a wire is gone, it's gone. But it actually is not completely true. Yes, once there's a break, there is a break. But before the break, remember, the electron wind pushes things this way. The back stress pushes things back. Now, suppose I take my laptop and I close it and I put it in my backpack. There's no current flowing through any chip or any wire anywhere, right? So the electron wind is off. There's just the back stress that gets things to relax. Right? This means that there is this EM recovery phenomenon, and that has not really been looked at to any great extent. There are some papers by Sheldon Tan's group that have looked at one version of this problem, but I think this is a sort of a significant degree of freedom. I'll skip that slide and go into this. One of the big things about electromigration is that it's a stochastic phenomenon, which means that process variations are going to affect it. The way that atoms diffuse, this is the structure, the microstructure of a wire. There are these grains of metal, and there are grain boundaries, and there are pathways for diffusion of metal atoms, one of which is through the grain boundaries, and the grain structure actually determines what this is. So this means that you can never kind of completely determine this, and there is this activation energy parameter, which is seen to be a Gaussian distributed parameter. So there's some nice work by Farid Najm's group where they basically built an EM analyzer and they put Monte Carlo around it, which is fine, because if your analyzer is fast, you can do Monte Carlo, but you've got to be able to do better. So it turns out that if we use that circuit interpretation, the RC interpretation that I talked about, the paper has an outline of a proof that if you find the moments for the model order reduction for the nominal case, the moments for the variability case are basically a constant multiplied by those moments. And I was trying to get my student to write this up. My student graduated. I don't have a student, so we just wrote it up in this paper. And hopefully someone can do something with it. And this shows you sort of what happens here. This is the bold curve is the nominal. The dotted curve over here is the Monte Carlo and also the prediction from something like this. And they are all pretty accurate. So there are things that you can do here that can make sort of a pretty a big impact, because you can do this very quickly. Now, the big problem here is that we have wonderful solution techniques, but if you don't have the data to go in, it's garbage in, garbage out. Today, all EM characterization is for the Black's law type of model, which is semi-empirical, et cetera. And so there's sort of a recent effort to try and see if you can have simple characterizations over here. And I'd like to kind of thank my collaborators for this particular piece of work. I stole the slide from them. So if you look at this thing, and if you plot the mean time to failure versus the length, it turns out that there's a relationship that looks something like this, which doesn't look like much. But if you look at the expression for the Korhonen's kind of stress equation, if this is the critical stress at which you have a breaking point, at that point, you have a relationship between various quantities, which is given by this closed form equation for a single line of this sort. So you could build a stress structure of this sort, and you could basically measure the JL product. You could measure the T-life, the lifetime divided, normalized by L square, and you could actually plot them against each other, and those points might end up being some kind of scatter plot. You build your best fit to this. When you build your best fit, you can obtain the unknown parameters over here, the unknown parameters which are this thing over here and this thing over here, and that, I claim, can help you solve the problem. Now, this doesn't seem very obvious, and it actually took me a long time to work this out after Suzanne sort of magically said this is true, and I was not convinced, but if you actually do the math, it's a very simple formulation. This is the original partial differential equation. This is the criterion for failure. Put in this substitution over here, and you get a new sigma prime thing, and now your failure parameter is this, which is exactly this thing that you pulled out of here. So if you have this failure criterion, and if you have this, which comes from here, and if you have your current density, which you know, then you can solve this, and now you have a pathway to go from characterization to this physics-based world, which was sort of impossible in the old days. Okay. So I have way too many slides. I've probably gone over time. So this is sort of me at the end of this talk, maybe you as well. I've tried to give a quick overview of this. This is basically sort of intuition, caveats, all the learnings in about 14 years that I've worked in this area. I spent the first 9 years making a lot of mistakes, and then only in the last 5 years did some of these things come about. And I've tried to put in, within this presentation and the paper, a lot of things that they don't tell you in the papers, things that have come through experience. So hopefully this is helpful to someone. Thank you.